Hey, Chemistry 30s, welcome to our new unit, which is dealing with equilibrium, acids, and bases. So outcome one here, we're going to focus on chemical equilibrium. Key word here, the root word of equilibrium is equal. So it means that having things equal, essentially. So we're going to talk about a few different terms here. So a state of balance is, as I just said, the term equilibrium. We can have a static equilibrium, in which nothing is moving or changing to create the balance. So, for example, you have a textbook sitting on a level desktop, so essentially a textbook on a desk. It stays motionless because you have two equal and opposite forces acting on it simultaneously. So we know that when a textbook's on a desk, we have the force of gravity acting on it as well as the force of normal acting on it as well. So that's why it's not going up or down. We also have dynamic equilibrium, which is a balance in which there is still movement, but no net overall movement. So the one example you would see in the completed notes is a juggler's act as a dynamic equilibrium, with some balls moving upward and some moving downward at any given moment. There's no net change because the rates of upward movement and downward movement are equal at any given moment. So chemical systems at equilibrium have constant observable properties, and nothing appears to be happening because the internal movement involves entities that are too small to see. So chemical equilibrium on the next page here. We assume that any closed chemical system with constant macroscopic properties, no observable change occurring, is in a state of equilibrium. There's three types of chemical equilibrium. First one we have here is phase equilibrium, which involves a single chemical substance existing in more than one phase in a closed system. We also have solubility equilibrium, which involves a single chemical solute interacting with a solvent substance, where excess solute is in contact with the saturated solution. And C, we have chemical reaction equilibrium. It involves several substances, the reactants and products of a chemical reaction. The terms forward and the opposite of forward, which is reverse, are used to identify which process is being referred to and are specific to a written equilibrium equation. The left to right change is called the forward reaction, so as we were seeing before, and the right to left change is called the reverse reaction. So reactions will often do an arrow like this to show that it can go either of which way. When a chemical system is in a state of dynamic equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. So rate is essentially how fast. The forward reaction equals the rate of the reverse reaction. And now we're going to talk about chemical reaction equilibrium. Chemical reaction equilibria are more complex than phase or solubility equilibria due to the variety of possible chemical reactions and the greater number of substances involved. To explain chemical equilibrium systems, we need to combine ideas from kinetic molecular theory, collision reaction theory, the concepts of reversibility, and the concept of dynamic equilibrium. So initially, we have hydrogen and we have iodine. Both are in their diatomic states. So we have H2 and I2. Initially, hydrogen, which is in excess, and iodine are added to the flask. The color of the iodine vapor is the only easily observable property. And then early in the reaction, hydrogen and iodine form hydrogen iodide faster than hydrogen iodide forms hydrogen iodine. Overall, the amount of iodine decreases, so the color of the flask contents appear to lighten. Both hydrogen and hydrogen iodide are colorless. At equilibrium, analysis shows that the flask contains all three substances. The purple color shows that some iodine remains. The consistency of the color is evidence that equilibrium exists. Forward and reverse reactions are occurring at equal rates. So essentially what we see is that we started off with this. We then were able to produce this product. And now all three of these substances are balanced. So our reaction is H2 gas reacts with I2 gas to produce 2HI gas. And then what we see is we can actually chart this. So we have our quantity, which is how much. Make a little note there. And this is our time. And so what we see is that over time, we had H2 and we had I2. And both of them are going to level off down here. So we have our I2 and our H2. HI, we didn't have any to start. What we see here at the bottom, we don't have any HI. Over time, as these two drop off, our HI actually begins to be produced. And what you will also notice is that this is at a temperature of 448 degrees Celsius, which is very warm. All right. Percent yield and position of equilibrium. Percent yield is defined as the yield of product measured at equilibrium compared with the maximum possible yield of product. The maximum possible yield of product is calculated using the method of stoichiometry, assuming a quantitative forward reaction with no reverse reaction. So we would essentially be saying that the one reaction we have is this one here. So the formula percent yield is our actual yield over our max possible yield times 100%. We've looked at this in chemistry 20. So let's say that the maximum possible yield we could have got is 4.0 grams, and we actually got 2.6 grams. We'd multiply that by 100%. And what we would expect this to be is probably about a little over 50%, but under 75%. So 2.6 over 4.0 is 0.65 times 100 will give us 65%. That is our percent yield. So if our percent yield is negligible, it means it's non-spontaneous, which means that no apparent reaction occurred. If our percent yield is under 50%, our reactants are favored. If it's over 50%, our products are favored. And if it's greater than 99.9%, then we have a quantitative reaction. We're going to talk a little bit more about this throughout. This is just kind of getting you a little bit introduced to it. That is the end of our first part of Outcome 1. Talk to you in Outcome 2.